Hello learners, this class is for 4th sem, second year 4th sem physics optics. So today's topic is determination of thickness of transparent material using biprism. So in the last class we have seen Fresnel's biprism, right? So in that we have seen that we can find out the wavelength of any light by using the Fresnel's biprism. So here also we are using the Fresnel biprism and finding out the thickness of any transparent material. Okay, we are using the transparent material. Let S1 and S2 are two virtual sources. Now we also know what are virtual sources, right? They are not actual sources. S1 and S2 are the virtual sources from where we can the light appears to be coming from these sources, but they are not actual sources. We have seen in the last class. Okay, actual source is S, not S1 S2. S1 S2 are virtual sources. Okay, let S1 and S2 represent two virtual coherent sources of light. They are producing the interference pattern on the screen. Okay, they are producing the interference pattern because there are two waves. There comes the interference phenomena, and due to that interference phenomena we can see the pattern on the screen. So at point O here, at point O, central bright fringes is obtained. Central bright fringe will be obtained as S1O, S1O and S2O are equidistant. They are equal. So we can see the bright fringe at O because the path difference is 0, no? From here to here and here to here the path difference will be 0. That is why we can see the bright fringe. So now let us suppose we are introducing a thin transparent film here. Okay, we are introducing a thin transparent material, like let us suppose some material of mica. Okay, that is introduced in the path of this light. This light is going in this way, no? In between we are placing the transparent material mica. Now then due to the differences in velocity of light, now the velocity of light changes. Okay, and the air also, the medium also changes. Okay, here the medium is air and here the glass, and again here medium, again air medium. Okay, air medium, glass medium, again air medium. That means the medium is changing and the velocity of air is velocity of light is also changing. Okay, because of the two reasons, and that means it is going from the denser medium to rarer medium. One is that reason, and the other reason is that the velocity of light also changes. So due to these two reasons there will be a shift of fringes. The shift will be upwards. So actually the first fringe should form here, but what happens, the first fringe should form here, the next should form here, and third one here, alternatively here, and so on up to nth width should be here, nth fringe should be here. Now when we are introducing this transparent film, what happens means this fringe pattern, the interference pattern will shift towards, now where was our nth last fringe, there will be our first fringe. The shift will change to the nth fringe, near the nth fringe. The first will shift towards the nth fringe. Understood? I can say this is our nth fringe when we are not keeping any transparent medium. When we keep any transparent medium in between, then this will become our first here. This will become our first fringe. Okay. Thus, on introducing a thin mica sheet, which is of refractive index some mu and of thickness some t, in path of any interfering beam, the central bright fringe gets shifted from point O to point P. Let's suppose P. Here P. It had shifted from O to P, which is originally occupied by the nth bright fringe. Now the first fringe is there. Firstly, nth fringe occupied this place, but after keeping this transparent material, here the first fringe will occupy that space. Now P is the position of the central maxima. Now this is the place of central maxima. Okay. Now here S1P and S2P will be equal. S1P and S2P will be equidistant. Equidistant. No path difference. Zero path difference. Okay. So this is what written here. You can read this. You can write the notes also. Now, as S1P is equal to S2P. Okay, so S1P minus T into mu of air plus T, the thickness of the transparent film, mu, refractive index of the transparent film, will be equal to S2P into mu of air here. Okay, so what we can write? We can write like this: S1P minus T plus mu T is equal to S2P into 1, because the refractive index of air is 1. Mu will become 1. Okay, this is 1 and this is 1. Now, S1P minus T plus mu T is equal to S2P. So, we can write like this: S2P, send this side, S1P is equal to mu T minus T. Okay, this one. What we got is this one. Now, T here, taking common. T mu minus 1. Let this be equation number 1. Okay, this is a path difference between two rays after introducing the transparent material. This is the path difference. Now, from Young's double slit experiment, we know the path difference at P is XD by capital D. Okay, let this be equation number 2. Now, we got two equations. This is our first equation, this is our second equation. Now, what we are doing? From 1 and 2. This is our first equation and this is our second equation. This is also S2P minus S1P. This is also S2P minus S1P, because this is also path difference, that is also path difference. Let us equate these two equations. First equation and second equation equating. XD by capital D is equal to T mu minus 1. What we want? We want thickness, no? We are determining the thickness only. So T is equal to, send this mu minus 1 this side. It becomes XD by mu minus 1 into capital D. This is our third equation. So by this we can find out the thickness of the transparent film. Okay. So in fringe width form, thickness T is beta is equal to lambda D by D. So from this we can write small d by capital D is equal to lambda by beta. Now we can put this in third equation here at small d and capital D place. So we will get T is equal to x by mu minus 1 lambda by beta. Okay, you can see here. Okay, this is the thickness. This is the thickness of the transparent material that is introduced in between the light, in between the path of the light. Okay, we have found out the T.